Welcome to Soli Gloria Physical Chemistry. This is the third lecture of Chemical Kinetics series. So today's topic is rate equation. We are going to solve differential rate law, which is normally differential equation. Then there are ways to do it. Basically, firstly, we do by hand, meaning analytically. So we try to solve the differential equation. But in your general chemistry even, or only physical chemistry, you have solved those first order, second order, and zeroth order differential rate law, so that you can plot the concentration as a function of time, and also you have dealt with lifetime. Not lifetime. Kind of half-life. I'm sorry. Yeah, things like that. So today we are going to do a little bit complicated, advanced matter of those rate equation. Firstly, we'll do reversible first order. It is still first order, but it is reversible. You have to consider both forward direction and the reverse direction, and also steady state with an unstable intermediate. It's kind of a little bit more complicated. And then second order reactions, okay? A plus B making product, and you have to consider both. And consecutive first order reaction, those things we are going to deal with today, okay? And also at the end, we are going to solve kind of reversible consecutive first order reaction as an example of a, let's say, complex system of reactions. Solve it by numerical integration using Python package or Python module and ODINT. Yeah, and I'm going to kind of let's say demonstrate it with Spider editor, a Python program or Python support program. Okay, let's begin. Okay, so this is where we are, and this is a kind of map for modeling a complex system of reactions. We have a system of reactions, and then we develop a set of differential equations for those, and then we are going to solve it. In order to do this, we have to fulfill the conservation equation, and then rate constant information. So assuming these done was applied, and then we are going to solve this. And first we solve this with analytical way, or then we use, which is much versatile, use kind of some software or numerical way. Solve this set of differential equation, and then we'll have a set of integrated rate law, which shows us a concentration of reactant or product as a function of time. And then, of course, then by doing experiment, we can also produce concentration as a function of time. Then we can compare those, and then any improvement or modification of the system or the rate constant. And then we iterate this, and then we can analyze the system of the reactions, and then draw some particular conclusion for useful application. So that's what you do. So this is the third part and the last one. So first one of this lecture, reversible first order reaction. We do usually A to product, but in this case A to product and product to the reactant. So the rate constant for the forward reaction K1, reverse reaction K2. And initial condition is that initially we will only have A, so A naught is the initial condition for A, and B naught equals 0, so no B initially. And then concentration of B is equal to A naught minus A, because there is a stoichiometric quotient 1 and 1. Okay, so this is the initial or kind of a conservation relationship. And this is then, we can write the rate law in such a way that dA dt, the consumption of reactant, is minus, because this is consumption, K1A, and production K2B. So this is the rate equation. So to solve it, we know this from here, and then we just put A naught minus A for B, and then we kind of gather the variables together. Minus K1, there is also minus, so K1 plus K2A plus K2 A naught. This is the constant then, and then we'll just make it as a kind of one variable. So we'll have K1 plus K2 as a factor, then we make this, and then this is actually the equilibrium constant is just A B over A, equilibrium concentration, and B is also A naught minus A equilibrium and A equilibrium. So this K, well, detailed balancing, micro reversibility, or whichever you choose, K equilibrium constant is K1 over K2. Okay, so we do some rearrangement done in this way. A naught over EQ is equal to K1 over K2. This is 1 and plus 1. So A naught over AEQ is K1 plus K2 over K2. Now AEQ is then reverse reciprocal of this, K2 over K1 plus K2, and A naught. Then we have exactly this one as here. So this is kind of neat in a way. dA dt is equal to minus K1 plus K2, A minus AEQ. Then we can integrate this directly, just as simple as just a first order reaction. So Ln, but in this case we have just the EQ part. So Ln A naught minus AEQ over A minus AEQ equal just the same as this, K1 plus K2T. Okay, so with this in mind, and then you can use this back and then rearrange this and then obtain A in this kind of form. So A as a function of T. So this is integrated rate law. Then of course then you can obtain B from this relationship. So like this. Okay, so this is done. I think this is done. Maybe some more. Yes. Yes. Okay. So this is done. And then this is plotted in the concentration A and B concentration. A concentration B. B was 0 at the beginning as a function of time. And then if you consider this as a first order reaction, the half-life is ln2, which is 0.693 over K, in this case usually K1. That's A's the half-life without reverse reaction, but there is a reverse reaction, so this is half-life. But that half-life is from A0 to A equilibrium, so between this half is here. Okay, so that's the half-life of reversible reaction. And then BQ is here, so half of BQ is also, these have not really half-life, but half in growing life. Yeah, so this is kind of one thing we can observe for first reversible first order reactions. And then second topic is the state to state unstable intermediate I. Well, it was a reversible first order reaction, but there is an intermediate in between. So there are 4 the rate constant K1, K2 forward, K minus 1, K minus 2 backward. Okay, and equilibrium, because this is unstable, state to state unstable intermediate, so K is A B over A equilibrium concentration, and then microscopic reversibility tells us that K2 over K forward over backward, K1, K2 over K minus 1, K minus 2 is equilibrium constant. Initial condition is A naught only. So begin from A naught here, and B naught is 0. Then at any time, A naught is the sum of A, I, and B, because all stoichiometric coefficient is 1. Okay, so this is the initial condition, and now we can write the rate law for intermediate and B, and then maybe you may do the same for A, but doesn't matter. So a di dt is production, consumption. So production first, K1A and plus K2B, yeah, and then consumption is this way, K1 and K2I, yeah. And B production is K2I, and consumption is B itself minus K minus 2. So I think there is a mistake here. Here is the minus sign here. Yeah, I'm sorry. And then steady state approximation is applied here, which says that the rate of the consumption or production dIdt equal 0. So this is equal 0. Then if that's equal 0, then we can obtain I as a function of A and B. So this is done. Then we can do dBdt. dBdt is, you be careful that dBdt is K2I, you use this for I, minus K2B, and then you will obtain this. Just to rearrange that, this minus K2B is this minus K2B. So firstly, actually one term, and then that you apply multiply K2. So K1, K2A was there. Yeah, just as doing this, K2 minus K2, K minus 2B is here, but you have this term, and that is negative. This is negative, and so that's subtracted out. So basically that's what is done here. Then which is equal to, let's say, K1, K2 over K minus 1 plus K2 as KF, and you see forward, backward. So this term K1 minus 1, K minus 2 over K minus 1 plus K2 is KB. It's forward rate constant, backward rate constant. Now we assume that, well, there's one case we are examining here. K2 is 0, so there is no go back, and K1 is much greater than K2, let's say. Okay, so it's not really making productive. So, but anyhow, then but if there is a channel to go out and that accumulate, then this goes to completion. And if the I equal to A is in equilibrium, then K1, that equilibrium, not this K1 equilibrium constant is K1 over K minus 1. Then the rate equation reduced to, because K2 is 0, there is no this term, and K minus 1 is much greater than K2, so we ignore that. And then we have K1 over K minus 1 is capital K. So now we have capital K over this term. But this is what? If K2 is 0, then that's exactly the same as Kf. Okay, so this is either this or K2 K1, this equilibrium constant, or KFA. So either way, this is reduced, very simple relationship. Now the next topic is that second order reaction. Well, it looks like first order for A and first order for B, and but together this is second order. This is not the same as A 2A goes to product case. So this is we call second order mixed case. Okay, so second order mixed case differential equation or rate equation is V equals 1 over, well, this is rate constant, whatever the stoichiometric coefficient there, 1 over A dA dt equal 1 over minus also 1 over B dB dt equal K A first order, B first order. Okay, so in this case, A and B are both 1. We can just utilize this dA dt or dB dt. So minus dA dt instead. Okay, and also the condition for initial condition is firstly it begin with A naught and B naught, t equals 0, and then A naught minus B equals B naught minus B, because if one consumed, also one be consumed, right? That's the relationship. And then B is rearranged to B minus A naught plus A. So this is what you are going to use for B. Then dA dt equals KA, and B instead of B we put this. So this is then ordinary differential equation only for A. Okay, so we rearrange that dA minus dA over A. Where is A? Yeah, A, and then B naught minus A naught plus A, just like that, and K dt. So this is just look like second order. This is second order in A, but it is a kind of a fraction. So you kind of separate, divide this fraction into two parts, and then assuming you have done that, the separation coefficient is C1 and C2. Okay, then find it. So when t goes to infinity and this goes to, or product, and A assumed to be 0, and then if A assumed to be 0, then what is done here, you multiply both sides with A, and then C1 A multiplied here, which goes to 0, and C1 times 0 is 0, and here you just kind of cancel A from denominator and numerator because you applied A here, and then A goes to 0, and then C is equal to B naught, 1 over B naught minus A naught. That is the relationship. And also you could do similar arrangement for A equals 0. A equals 0 is that you A equals 0 that so rearrange that, you obtain that C2 equals minus B naught minus A1 A naught 1 over B naught minus A naught. So C2 equals to minus C1. Well, it might be that clear, so I would explain again. So actually you just to make a common denominator A times this term, and then you multiply this with C1, multiply A with C2. Then you see C1 is, then you multiply this with the denominator is the same, so which is equal to 1 is equal to C naught times this, and then C2 times A. So C1 is B naught minus A naught, which is this one. So that is 1. Okay, this is different. And then B naught minus A naught over 1 times A. And then which is equal to C2 times A. So 1 is here, plus 1 plus what was there is 1 plus 1 plus A over B naught minus A naught. And then here A is here, C2A. So which 1 is closed in both sides, and 0 equals to A over B naught minus A equals to plus A plus C2. So A closed out, and then C2 equals to minus, because this term will be kind of moved to the other side, which is minus B naught minus A naught, which is C1. So C2 minus C1 is there. I'm sorry, it's just kind of. Okay, so you separate the differential equation, and then the fraction, and not the differential equation, in two parts, and then this equal to that. And then you can integrate this separately, because there's a plus sign. Then you obtain first term, and the second term equals kt. And then you make them, kind of put them together, because both this is common factor. So you put it, then log minus is kind of the log fraction. So that is done this way. It's kt. Then somehow you make this rearrangement into simple form, which is kt. Okay, so this is done that way, and then well, that's done that way. And also consecutive order reaction. This is probably the last topic for the simple terms. And then this A1 make A2, and this is an example, the simplest example of reaction system of system of reactions. So one reaction and two reactions, and they are connected, of course. A1, A2, and A3, and the rate constants K1 and K2. So initial condition is A1, only A1, and no A2 and A3. So at any point, so the concentration of A1, A2, A3 equals to A0, A1 naught. Then the rate equation for this system of reactions is dA dt is minus consumption, and dA2 dt is production and consumption. K1A minus K2A2, and this one only production, K2A2. So this is a linear differential equation, and 3 must be done at the same time. So this one is just a simple first order reaction. Remember that this is the differential, this is integrated rate law. So this is done like this, and then once you have A1 solved here, then you can solve this, and then you notice that this is a linear differential equation of this type, y prime plus p y equal q. So the solution for that is, we know as a kind of formula, y is e to the integral p dx integral q e to the, this is minus, but plus p dx and dx plus c. So you put a 2 here in this way. Well, actually you arrange this in this way. So y prime, y, and some other function. So in this case, y prime plus ky plus q function. So this is q, this is y, k2 is y. So a2 itself equals to integral minus k2 dt, integral Now k1, this cube function, a1 naught e to the k1t, just this function, and then integral now this time is plus k to the t, and integration constant c. Then if you integrate this what you get is e to the minus k 2t. Yes. So you have this k to t, but here you have e to the k 2t. This is minus and this is plus, so that will cancel each other, and then you have only this to be integrated, and then that is firstly you have to integrate this and then cancel. So which is k1 plus k minus k2 minus k1, k2 minus k1, so which is goes to denominator, and then k1 just a constant term, and e to the minus k1t e to the plus k2t, but we are here e to the minus k2t here, so that's cancelled, and then you are here with this multiply this, and then initial condition tells you that 0 0, and then a2 a2 is 0, so c is just this one, but plus this equals 0, this is minus this, so there is minus sign. Okay. Minus of this is the c. So we a3, okay, now we obtain a1 a2. A3 is just from this conservation equation, so a3 is obtained as a1 naught minus a1 and a2 here, and then we obtain this for a3. Okay, so we have done this, and a1 a2 a3 all as a function of t, so integrated rate law for the consecutive first order reactions. So the conditions is the k1 equal 1 per second, k2 equal 1 per second. So k1 k2 equals the same, and then a1 reduces and a3 accumulates, a2 just grow first and then reduce, and then if k2 is faster than k1, then this consumed much faster, so this a3 grows faster and k2 not really much, because it consumes fast, not really grow much. So so k2 is 5 now, and then you see this, and even 25 much faster, and just b is very small in concentration, but and a3 grows faster than the previously. So you see how it works. Okay, the last one is rather challenging. Consecutive first order reaction, but those are reversible, all reversible. So a1 goes to a2 and a3, but there is a reversible reaction. We put the rate constant as k1, k3, k2, k4. Okay, and maybe we did k1, k2, k3, k4. Yeah, either way. Yeah, k1, k3, k1, k2, k3, k4. Yeah. Okay, so with this method, and for a1, the rate equation is minus k1a and plus k2 a2. Yeah, minus k1a1, k2 a2. A2 itself, we do first production k1 a1, production k3 k4 a3, and then consumption k2 plus k3 a2. Yeah, so this is the right differential equation, and for a3 production and consumption, so k3 a2 minus k4 a3. Okay, so solve this, but it is rather challenging by doing pen and paper. it's difficult, probably not so difficult, but kind of very difficult at this point, doing analytically. So we are going to solve it with Python, with the help of Python program. And then this is, as I said, a kind of simplistic example of system of reactions. And then you could do much complex system like that, similar to extended or expanded of this. And also, this type of rate approach is very versatile. You can apply to even biological or system biology problem, maybe, or sort of things. So it's very useful, very handy to learn. And so with Python, we are going to use ordinary differential equation integrator, so ODINT, which is from SciPy, I guess it's scientific pi, SciPy integrate package or integrate module. Okay? So there, and the calling sequence or this module ODINT, first we give function, which is a derivative actually, and then initial condition and time span, and then argument for the function. So what it does is that it solves the initial value problem, just to our problem, for steep or non-steep system, versatile, of first order ordinary differential equation. Actually, it is using also it's a kind of legendary Fortran code for solving first order ordinary differential equation. So functions is a callable. We'll define it as a as a function. That computes the derivative of y dy dt. But that could be not just one single function, but could be the kind of y1, y2, y3, just like that. So y0 here is that array, initial condition of y, because it's array. So this function could be an array of functions, and t is a sequence of time point for which to solve for y. Okay, and argument is a Python language. It's a tuple. It's a set of numbers or something, pointing the numbers. That's the argument for this function. So with this in mind, we'll use the kind of let's say call ODINT with the derivative of these, and then W0 is initial condition. Probably I will do just 1 0 0 like that. 1 0 0 like that, and then time span is the time point we are going to use, and then k1, k2, k3, k4 are all rate constant here, and then this will be coded as drdt, derivative. Okay, and then the result is that the k3, all k1, k2, k3, k4 equals 1 per second. Then that is kind of a1 just reduces and a3 increases, and also a2 is accumulating somewhat because there is a reverse reaction. And also, but if k3 is getting dominating, and like all k2, k1, k2, k4 equals 1, k3 equals 3, then k3 a3 outgrows over a2. And also, if we increase k3 further, k3 do outgrow over a2 this much. Okay, so that's what we are going to observe when we solve this equation numerically. Here I open the spider editor, which is equipped with Python 3.7, and I loaded the kind of code. I just wrote it. Well, actually, this is done last year sometime, and then it is on probably the English speaking student or might not really access easily, which is Naver, N-A-V-E-R, naver.com. There is a cafe. It's a kind of interest group, internet. I say, let me just type somewhere. Probably I can do it here. Yeah, it's cafe.naver.com/SDGUC. So this is the cafe URL. So there you would find the code and kind of everything. So I am trying to solve all computer problems of Sylvie Albertin-Bauwendy's Physical Chemistry 4th edition. I've done just I think 3 or 4 chapters only. Well, time is really budget here. So anyhow, there you can find this code and and then other problems too. So firstly, this is there is a chapter 18 problem B. That's the same as our consecutive first order reactions. So firstly, we are going to import some modules. So NumPy as NP and SciPy integrate as import ODEINT. From SciPy integrate the module, we import ODEINT, which is the first order ordinary differential equation integrator. And then we also, in order to plot matplot library pyplot as PLT. So first we import the packages we need, modules we need. That's the Python language. And then we first define the derivative function. So this is actually the rate law, and which has some argument. So W is our condition, and T is the time point, and K1, K2, K3, K4 are guess rate constant. And then we actually AX is A1, Y is A2. There is no really laser pointer here, unless I found one. Maybe I'll try. There we go. I got it. So the firstly, X is A1, Y is A2, Z is A3. Okay, so the initial condition is given here, or the current condition is given here, and then because it is integrating point by point, and then that is X and Y and Z's initial point for, or the condition for the current time, and dx dt in the code like this, minus K1 X excuse me, minus K1X plus K2Y, okay? And then dy dt is production K1X minus K2 plus K3Y plus K4Z. And dg dt is K3Y, yeah, minus K4Z, just like our differential rate law. And dw dt altogether, because this is return. dx dt, dy dt, dg dt. So we define functions to be used for ODEINT, just like that. And then, okay, so firstly we define that, and then we also define this kind of way, how much we are going to use. So number of point, 301 point we are going to plot. And then this NumPy's linspace makes this time point is that 0.3, meaning is that I think it's 3 seconds. So 0.23 seconds with 301 evenly divided a point. So actually then from 0 to 3, so there are 301 points. Okay, so that's your t axis, and then for that you also for each time point you will plot the concentration of x and y and z, which is A1, A2, A3. So we call it for some reason, I'm not sure why, ABC, A1, A2, A3. Yeah, I think that's to make differentiate from the function and you know, the in the color. So just like the same shape of array A and B and C is done here. Okay, and then I think I have to just remove that. And then what we do here, rate constant x k1, k2, k3, k4. Firstly, we'll do just 1, and then it could be 3 or 9 in the later. Well, this pound percent is actually define a section in the code, so you can run whole code from the beginning to the end by this run, or you can run current cell. So this defines a cell. Okay, cell by cell by this button. Okay, so we'll just do that by this button. Follow my cursor. Okay, so we first define this in this section, and then this is what really does this does the integration. So you see A1 equals 0. This is the kind of initial condition, you know, initial condition for this problem. It could be different, but anyhow, so W0 is the initial condition for A1, A2, A3. So it is 1, 0, 0. So how it is done is that this is an array of 3 elements, 0, 0, 0, and then it is replaced. The first one is replaced A0, which is A0, which is 1. So W at this point is 1, 0, 0. In the array, in the Python, the first element of the array is indexed by 0. So, you know, and then this is your initial condition for, actually the initial condition for A, B, C. Okay, so that's what it is. Okay, so that's once done. Once done. Okay, then what it does is that the kind of for loop is here 1 through n, 301. How it is done is firstly time span is calculated. Actually, that those are the same. Time span is given here, and then we call ODINT with the derivative is defined above, and then W0 or 3 point, and then the array, and then T span and argument K1, K2, K3, K4, and then it is called ODINT will solve that, integrate that differential equation, set of differential equation, and then we'll return in W. That W has the derivative part, and then the derivative part is assigned to integrated part, actually integrated part assigned to this. So this is not 0, 1 through n. So W1, 0, 1, 2 is cumulated here. Okay, So that's how it is done. And then now W0 becomes to W1 becomes to W0, and then it iterate this way. So this is the way we solve the simultaneous a set of differential equation. Okay, so once it is solved, now what is done? The last section is to plot by using PLT, the plot library, matplot library, plt.plot, plot, y label, x label, and legend. So and show. So this is the routine for plotting. So A as a function of t, B as a function of t, C as a function of t. Okay. So and also the label is A, B, C, but which is A1. In this case, A1, A2, A3, just like that. Okay. And then label concentration y-axis and time is the x-axis. Okay. So basically, I just explain what the code, how it looks like, but it's your job to practice and then develop your skill and get used to with this and use it as often as you may. You know, at any time you have some opportunity to code, that's a really good habit to learn. Okay, so next step is to run the code. Okay, so we'll just firstly run everything and see how it works. So this is what we expect for all what here x1, k1, k2, k3, k4 are all ones. Okay, now a technique is that we can either replace this to k3 equals 3 and rerun. Maybe that's neat. Okay, that's what we'll do. Okay, just make 3 and then we'll just run everything. Then it is done. You see that, compare this, that this is k3 k3 3. So it kind of A3 outgrow over A2. Of course, the A1 decreases. Okay, and then here a trick for that is if I say K3 equals to 9. Okay, it is done. And then I don't have to run up to here. Only I'll run from this section by using this button. So I'll just click, and then that is run, and then we'll just run the plotting section to see what happened. Okay, so then A3 much outgrow over A2, and A1 decreases as before, but faster. So compare this and that. I may increase this line for a little bit more. They should be done that way, but okay. So basically, we just have used the Python, and there in Python we also use NumPy, SciPy, and plotting library to solve a physical chemistry problem, chemical kinetics problem, or I would say a system not really that complex, but a complex system of chemical reactions. Okay. And then let's go back and then remember with late Professor William Gardner, the flame C1, C2 system, and that has many reactions involved. You collect, for example, you collect all the rate constant data and all other information about, initial concentration as such, and then you code this, and then you may run and analyze the flame kinetics. You may do this for your own research problem, and also maybe biochemical or all sort of complicated things you may solve with an aid of Python and efficiently and more clearly. Yeah. Thank you for being with me, learning chemical kinetics by 3 parts.